Okay, so we are very happy to host Dominik today, who works in a computational social choice. Dominik, the floor is yours.
Thank you very much. Thank you for the invitation. So I work at Lamsad in Paris Dauphine for the last 2.5 years. This is a project that started with Thomas Wons, who was a postdoc at Lamsad for several months, but is now departed to Oxford. And with Patrick Lederer, who was then a PhD student at TU Munich and is now in Sydney. Okay, so this is about the Squared Kemeny rule for averaging rankings. What's the kind of problem? Oh, this used to work. What's the kind of problem we're looking at? It's about aggregating rankings. So the input to our problem is going to be a collection of rankings, and the output is going to be a single ranking. So here's an example. There are 4 alternatives, A, B, C, and D. We have a bunch of rankings. That's the input. And then the output is going to be a single ranking. Now, sometimes there's not enough information to choose just one ranking, and there will be a tie between several rankings. But that's our goal. And I will refer to this kind of thing, a collection of rankings, as a profile, a preference profile, or ranking profile. And also I will allow there to be weights, which will be useful in some applications. Okay, and so how can we do this? There are several methods that are well studied for this problem. It's called rank aggregation in the literature. And probably the best known example is the Kemeny rule. Kemeny was a Hungarian mathematician who proposed this in 1959. And it's a very simple rule. It just optimizes over the set of all possible rankings, particular objective function. And the objective function is just that we are going to minimize the overall distance. So R is going to be our output ranking. Ri is an input ranking, and the distance between the two, and we're going to minimize the sum of these distances. Now, what's that distance between 2 rankings? That's the so-called Kendall-Tau distance. That's the swap distance, or bubble sort distance, has many names. And it's just the number of pairs of alternatives on which the 2 disagree. That means that the output ranking puts A above B, but the input ranking puts B above A. And that would be sort of one thing in which they differ. And the distance is how many of these pairs there are. Okay, so this is the Kemeny rule. It minimizes this quantity. Okay, is this a good, yeah?
In your example, is it the Kemeny winner or not?
I haven't actually computed this. I should have.
I don't think so.
No.
But, C should be higher, I guess.
C should be higher. Yeah, well, maybe. Exercise.
Easy exercise.
So I actually know some websites where you can put this in, but oh well. So, but let's now look at an easier example where we can actually compute it in our heads, and that's the motivation for this paper. So suppose we are an online hotel booking agency such as booking.com, right? And there you can search for hotels. And then it will give you a list of hotels, and you can choose to sort them by whatever criteria you most prefer. And so there's things like price, or the distance from city center, or property rating. But then booking.com actually gives you some other intriguing options, such as best reviewed and lowest price, which suggests some sort of aggregation of these 2 criteria. Okay, so indeed, you could take a bunch of hotels. These are actually hotels. This was presented at the EC conference this summer in Yale in the US. And these were actually the hotels that were available when I searched for where to stay during the conference. And this is then ranked by price. The La Quinta was the cheapest one. The study was the most expensive one. And so this is the best hotel. But if you rank them by score, then the cheapest one is actually the worst one. Okay, and so if you're clicking on this best reviewed and lowest price, then we'd expect some sort of aggregation of these 2 rankings. And Indeed, one could even imagine this user interface to be a bit more advanced and allow you to actually say, what's the weight on these two rankings? And so this is going to be this one up here. So this is 100% on the price. Then, of course, we should just give the price ranking, 90% lower, 10% on the price, and therefore 90% on the score. Okay, so now let's put this into the Kemeny function, right? And ask it, what's the Kemeny output? If for example, I take 70% of the price ranking and 30% of the score ranking. So does anyone have a guess?
Yeah. Yes.
What the outcome would be?
But I will be abstract, so.
So it's actually quite simple. This is the outcome. Whenever the percentage is above 50% for price, it will just copy exactly the price ranking. And if it's less than 50%, so more than 50% for the score, it will just exactly copy the score ranking. And the only interesting case is the 50% case, where there's a kind of tie between the two the two extremes, but it's only at exactly 50-50. And why is this? This is because Kemeny is a Condorcet style rule. So if you have a majority for something, it will follow that majority. Or you can think of it as being a median. And if you take the median of a bunch of numbers, but half of the numbers are the same number, that's the median. Right? And so, in fact, if you click on this, at least for the case of New Haven, Connecticut, it seemed to do something like that because it was indistinguishable from, I think, the score ranking. It was just best reviewed, and price did not actually make any difference in that search. So this is a bit of a problem if you use Kemeny. Kemeny is the most popular rank aggregation mechanism, but certainly it seems to not be fit for this kind of purpose, right? You tell it, oh, I care 70% about the price. It throws away your 70% and replaces it by 100%. That's not what you wanted. You want the price ranking to have kind of 70% of the influence. Okay, so what kind of method could we use that actually does do it correctly and really mixes the two extreme rankings? And that's going to be the Squared Kemeny rule. Okay, and it's actually less well known, but in the same paper from 1959, it's a fun paper trying to bring mathematics to the public and do some sort of fun exercises, but in particular, it considers this rank aggregation rule. And Kemeny actually gives two different rules. One is the one that we now call the Kemeny rule, and he calls it the median rule. And the other is the mean rule, which we've now decided to call Squared Kemeny. It's the same rule. We choose a ranking by minimizing over the set of all rankings. But this time we take the distance and square it. So this means if you're further away from a ranking, then it's costlier and costlier and costlier the further away you are. So we're probably going to try to more equalize the different distances. So the median doesn't care as much. If there's some people are very far away, but some people are very close, that's great. Then the Squared Kemeny, that would not be as great. And if we plug in this example into the Squared Kemeny rule, then this is the outcome. And intuitively, it does more of what we want. So for example, the La Quinta in here, it smoothly travels from the top to the bottom.
That's some strange things as well. Like Omni.
Like Omni, right? It goes down and goes back up. Yeah. That's
Since
right.
it's a ranking, it's not necessarily that strange because you can be worse and worse, and at some point La Quinta becomes even worse.
Yeah.
So non-monotonicity is not necessarily annoying in that case.
Yeah, but it's strange.
Yeah, it's intriguing.
It's a bit strange. Yeah, I agree. Okay, and I should also qualify this because actually at every step here, there's a big tie. There are many rankings that are selected by Squared Kemeny, and I've chosen specific ones here that make the picture look nice. Right? This is an artifact of there being only two different rankings in the input. If we had more than two, then the number of ties would drop a lot. Okay. Now it is non-monotonic, by the way, but I think it is what's called single crossing still. Right. So for example, the study starts out below Omni and then they cross, but they never cross back. Right. So And that would really be
But up to ties,
that.
yes. With ties, you may have things like that.
With ties, yeah. So,
But if you break that correctly,
but there's always a choice of intermediate rankings that will be single cross.
like you have a static type breaking rule. And,
yeah, exactly. Do something like take the one that's closest to one of them or something like that. Okay, so this seems promising. So let's study it in a bit more detail and see whether it actually does the right thing apart from this simple example. But we'll first stick a bit simple, but actually before we analyze this rule, let me just say that this is not just about hotel booking, but the same kind of problem you could apply in many other rank aggregation tasks. So for example, well, this is the same thing, but not hotels, but other online shops where you need to sort things. You could consider news feeds of social networks. You remember when Twitter was changing ownership recently, there was a big one of the big discussions was over the For You feed versus the following feed that gives you a chronological order. So do you want the reinforcement learned engagement maximizing feed or not? Right? And I frequently switch between them, and maybe I would like a toggle that says how much are you allowed to boost things that I will probably like? How much do you want a chronological one? You could mix them. You could consider university rankings. So if you take a university ranking, typically there are sort of sub-rankings by research, by teaching, student satisfaction, etc. And how do you combine such criteria-based rankings? Now, in many of these situations, actually, you might object and say, really, we're not aggregating rankings here, but these are numerical, right? So even here, the price ranking isn't really a ranking. And in fact, the La Quinta was sort of in the $300 for the conference length, and these were more 700 to 900 each. So there's a big difference that the ranking obscures. Similarly, the scores here, they are also numbers sort of between 5.8 for the La Quinta and up to 9.2 for the graduate here. And so maybe the better way is actually to average those numbers somehow, and that's the better way to aggregate these two criteria. But I'm not sure about that because the first price is denoted in dollars and the rating is not in dollars. You have to somehow normalize them together. Then even worse, price, the higher numbers are worse, and rating, the higher numbers are better. So you have to flip it, or do you do one over it, or what do you do? So there are lots and lots of choices, and that you probably have to do ad hoc every time. Right? There's no thing you can write down. I mean, you could try, but in general, there won't be one way. And this one is at least, it's not ad hoc at all. You convert to a ranking, and then you can just plug it into Squared Kemeny. And the same thing for university rankings. Again, student satisfaction, percent of students employed after graduating, research outputs in citations or papers or whatnot. These are all numbers. Yes, you could take a weighted average, but these are all different numbers types. So maybe going via a ranking makes it less arbitrary. Here's a different type. So these are all kind of criteria and merging rankings from criteria, but there's sort of a single decision maker that decides what are the weights. That's the aggregation. But I come from computational social choice, and where we mostly think about voting problems or collective decision making, where there are several decision makers with different preferences. And there are some applications in this frame of mind where these rankings come from different people, and they have an interest to have the output ranking be similar to their ranking. So for example, suppose you have a hiring committee and you want to hire maybe one person, the method de conférence position or something like that. You have candidates. Each person on the hiring committee ranks the candidates, or the hiring committee has to rank the candidates. That's the output. Right, but there are also inputs because the members might disagree on the ranking. And in particular, you might want to not use something like Kemeny, where it sort of copies the biggest part of your committee. If you have like 50%, 51% of your hiring committee comes from one area, then and they all vote the same over the candidates, then all the rest of the rankings would be ignored by Kemeny, for example. So in Lamsad, where I'm from, we have sort of three subgroups, pôle 1, 2, 3, that are on different topics. Like I'm in the decision one, and 2 is combinatorial optimization, 3 is machine learning. But we are the biggest in the first poll, 60%. And so if there's someone who comes with a social choice, probably all rank them top, and we're never going to hire a machine learning person. But we actually want to split it proportionally. And so this is why a rule like Squared Kemeny could make more sense. It could also be the case in sort of low stake situations where you want to aggregate different people's opinions. For example, a group of friends. Maybe in a group of friends, it's not actually appropriate to do a majoritarian type of voting rule. Just because 3 out of 5 friends agree doesn't mean that you should always follow their opinion on everything. You need to compromise. In fact, in the literature, Kemeny is often called as the compromise rule. But in this frame of mind, it really doesn't feel like a compromise at all. It's just a decision, but it's not really combining things very much. Okay, so these are applications where this idea of Squared Kemeny might make more sense. So let's analyze it formally a bit and try to say why it does the right thing, why it really averages rankings rather than taking a median from it. And so one is just a generalization of what I showed you at the start. Let's think about profiles in which there are only 2 different rankings mixed with some kind of weight. Okay, so and we make this into an axiom that we call 2 rankings proportionality. And it talks about all profiles that consist of just 2 different rankings with weights, sum up to 1. And let's suppose that these 2 input rankings differ on D pairwise comparisons. So the distance between those 2 rankings is D things. Then what's the correct thing for our rule to do? So given this kind of input, we put it into our aggregation rule, then it should output all rankings such that the number of agreements between one of these 2 input rankings and the output should be proportional to the weight of that ranking. So this is maybe a little bit hard to pass. So let's go to an example. Suppose we have 2 rankings. They have weight 70% and 30% respectively. And suppose these 2 rankings disagree on 10 pairwise comparisons. Then the output ranking should agree with the first one on 7 of these disagreement comparisons, and with the second one on the other 3 comparisons. That's what this axiom says. Let's see. And this example is actually, these numbers are chosen strategically because here, if you look at these 2 rankings, they disagree on exactly 10 pairwise comparisons. And as we move from left to right here, in each step, there's exactly 1 swap that changes. So if we're here, then this 70% one agrees on 7 out of the 10 disagreement pairwise comparisons with that, right? So it agrees with 7, it disagrees with, Marcel being above Omni and Steady being above Omni, and Marcel being above Omni. So these are 3 pairwise comparisons.
Just to check, in your property, you don't have any slack. Like if it's 7, it's not 8, not 6, it must be 7.
And even more, we say exactly the set. So you're supposed to take all of them.
Okay.
So whenever you're in the 7th position, you have to do all of them. So this axiom actually forces you to have these ties that I mentioned. And then there's this rounding function here that's also perhaps controversial. So if you're at 7.5, you see it, right? 75%, but 75 times 10 is not an integer. You need to round it. For 75, actually, that would contain 2 numbers here. Okay, so definitely you can think of 1,000 weakenings of this, but why do we make a strong axiom? Because it appears in a characterization result, and so some strength helps us obtain it. So why is the Kemeny rule so popular and so widely used? One of the reasons is this paper by Peyton Young and Arthur Levenglick from 1979, in which they give an axiomatic characterization. So that means they consider the class of all rank aggregation functions, and then say that the Kemeny rule is the only one that satisfies this list of 1, 2, 3, 4 properties. So it's the only one that's anonymous and neutral. So that means it doesn't depend on what you call the rankings or what you call the alternatives. Satisfies the reinforcement property. I won't explain in much detail what that means, but it means essentially if you have one instance where you have a particular output and you have another instance where you have the same output, if you put those two instances together, then you still have that output. Kind of consistency notion called reinforcement here, because this kind of reinforcement, like here, we think this is the best ranking, and here we also think that same ranking is the best ranking. So if we put them together, these two reasons kind of reinforce each other, we should still pick that. And optimization style rules such as Kemeny and also Squared Kemeny will usually satisfy this, and it's easy to see that they do. And then they have what they call the Condorcet property. This is roughly what I mentioned at the start. If you have weight more than 50%, then the output ranking should perfectly agree with that 50% input ranking. Actually, if you look into the paper, this property is super strong, super weird. It contains the quasi-Condorcet property, which talks about what happens in the case of ties. It's a very strong and artificial axiom, and some people sometimes think, oh, it has this nice name, Condorcet, therefore it must be a nice axiom. Not really, but yeah. So this is their result, and actually they also sort of in passing they say, well, yes, Kemeny had two ideas, the median rule and the mean rule, but the mean rule is completely uninteresting because only the median rule is this Condorcet style rule. I sort of diss it and thereby killed it. So we found no one in the literature that has looked at the Squared Kemeny rule after 79. Anyway, this is why we're doing it now. And we actually give a similar axiomatic characterization that also uses anonymity, neutrality, and reinforcement. And another technical condition of continuity. It's very mild. But we replace this Condorcet property, which remember says if a majority, then you copy it, by this proportionality property that says on the special cases where there are just two different rankings, we want to proportionally interpolate between the two. And so this is sort of where most of the pages of the paper get spent, because such axiomatic characterization results typically are quite involved. There's lots of hyperplane arguments in the space of all profiles. But anyway, it's true. And so Squared Kemeny is, in a sense, the correct analog of Kemeny if you want to have something like this two rankings proportionality. Okay, so this is for the case of two rankings. But what about three or more rankings? Does the rule still make sense here? And there we don't have as clean formal results. Let me just tell you a bit about what we do have. First, what we can do is we can just take three random rankings and then use different weights. And then we can draw a picture of what's the output ranking. And so here we took three particular rankings on 8 alternatives. And then first we look at Kemeny, we look at the simplex of possible weightings of those three rankings. And then the color is, it's more cyan the closer you are to the first input ranking, it's more yellow the closer you are to the third one. And magenta, the closer you are to number 2. And we see that Kemeny, if you're mixing it almost equally, then it takes a particular one. Otherwise, it just copies perfectly these extreme points, matching our intuition. Whereas Squared Kemeny, you see there's more of a gradient. The higher the weight goes, the closer you move towards that ranking. So pictures like this somewhat support the idea that Squared Kemeny does more interpolation. But this is just an example, and to be honest, it is cherry-picked to look pretty. So I looked through many of these triples of rankings, and this one looked best. So this is still not really convincing. Here's a more general worst-case way of looking at it by drawing what we internally call an alpha curve. Here's how it works. Suppose we have a profile, and I tell you about that profile that an alpha % of the voters have the same ranking. And then I ask you, how far away from that ranking can the outcome ranking be? And so let's start this for Kemeny. Suppose I have this alpha is less than 50%. Right? For example, it's 40%, and 40% of the people have the same ranking. then it could be in the worst case that the other 60% of the opposite ranking, and that would be the outcome ranking. So in the worst case, you're maximally far away from the input ranking. But once you go over 50%, then no matter what the others do, you're guaranteed that the outcome ranking is exactly equal to your ranking. And so it goes down to 0. And for Squared Kemeny, that's not the case, but rather the maximum distance it can be away from you goes down roughly proportionally as the size of your own ranking goes up. Yep. Yeah. Okay. So our input is an alpha number. And then for fixed alpha, for example, 20%, I'm looking for the worst case profile where 20% of the weight goes to a single ranking. And I look how far away can the Kemeny ranking be from that 20% ranking. And it can be the reverse. And so its normalized swap distance is 100% of the swaps disagree with me. But once I go above 50%, then 0% of the swaps disagree with me. Whereas here in Squared Kemeny, if you have 20, let's say 40% of the weight, then the distance of the output ranking to you can only be, and disagree with you on 60%-ish of the swaps.
I have two questions.
Mhm.
First one is, how do you compute the curve on the right?
Mhm.
Because the left, it's easy, it's
Yes.
straightforward.
Yeah.
On the right,
Yeah.
How did you compute the worst case?
Right. The answer is, so this is, it says hopefully for 6 alternatives here. So this is actually kind of a finer problem.
Six is me.
So 720 rankings. And so it's actually an ILP. So for roughly, let's suppose I fix an alpha, then I can write a program where I say how frequently do each of these rankings appear in my profile. These can be fractional variables. What are the weights of all the rankings to maximize this distance?
And my second question is, am I wrong, or do you have kind of asymmetric thresholds there? Like you need to have at least a small collision to start being able to change your
So this has annoyed us a lot.
Yeah.
You are completely correct. There's this kind of hump at the start. Yeah. And until we are at about 17%, there's no guarantee. You're 17% of the population, and you can still be completely opposite. Yeah. And 17% is enough to really deserve intuitively to not be reversed entirely, because for 6 alternatives, let's do this. How many pairwise swaps are there? 6 times 5 over 2 is 15. Some people have this memorized for quicker arithmetic. And 15, and 1 divided by 15 is less than 17%. Much less.
In fact, it was just because I counted the number of steps to
check
that it was 15.
Yeah. Good. Yeah.
Can it be more smooth?
No, it does need to be a step function.
Like a mirror in point.
Right.
Mirror in point.
So I'm not sure what you mean by smooth. So it has to be, like, it's actually a proper step function. This is like probably the wrong way to connect these points. It should be like, because this function can only take integer values, and I normalize them by dividing them by 15.
And practically analog with respect to cross-involving functions. So it will be the normal threshold function and the sigmoid function.
Right.
And I'm trying to keep it similar.
Yeah. So for a rule like Kemeny, these majority-based rules, I mean, that's just how they behave. If you're epsilon below 50%, you're completely ignored in the worst case. If you're epsilon above, you're guaranteed to always be completely followed. Whether there are analogs of it that make this, I mean, you're asking mainly about this picture, right? Whether you can make this at least a little bit less abrupt. I haven't seen such things in social choice. Maybe you can.
And for the right figure, is it also true that the worst case is when all the other voters have the opposite rankings? Or?
No.
No,
No.
Too simple.
yeah,
So-
it is.
You can imagine we've spent a lot of our efforts on this point here, looking at the profile that witnesses it, where 17% of the voters agree, but the opposite happens, and it's a complicated profile. There are, I think we need at least 15 or 20 different rankings of the 720 possible ones to make such a profile. And we've visualized it in many different ways and no success. So it's really, so my co-author Thomas Wons, he has very geometric intuitions about this and thinks of the space of rankings as kind of a sphere.
Yeah, you the
And-
permutation.
A permutahedron, and you have kind of these attractors. Like, so he has like some, it didn't shock him totally that there was a hump, but we can't really nicely explain it at all.
The fun thing is with asymmetric, like
Mm.
if you want to have complete domination,
Mm,
even one guy
Yeah.
stop you from that.
yeah,
So you
more
need to-
like 1/15 probably.
yeah, one
something,
something.
yeah.
15. So it costs more yes to start avoiding being completely overruled
Yeah.
than to overrule everyone. So
Yeah.
Mm.
Yeah, but I suppose it's because the square function is also not
yeah.
symmetric at all.
Hmm.
Okay, so this is, I mean, it shows that squared Kemeny is more proportional certainly than Kemeny, but it's not perfect. Now, but this is only for 6 alternatives. What about other numbers of alternatives? I think you can compute this for 7, but I'm not sure. I mean, if I could compute it, I presumably would have put it on the slide. So maybe 6 is the end. However, we were able to give some bounds on this function. So in particular, we derive this expression. This is mostly by reasoning about simple profiles, such as where alpha have the same and then 1 minus alpha are the complete opposite. And so we definitely know that squared Kemeny does better than this blue curve. But it's pretty loose. And indeed, this implies that the hump cannot be bigger than 50%. So this result says if you have 50% of the rankings, then definitely not the opposite of yours is going to be returned. Actually, it's much better, but who knows what happens for large M. You have a different bound that's more difficult to explain that actually shows the hump is less than 1/3 in width. Okay. I skipped a slide earlier here where I can do a bit more axiomatic comparison between the two rules, Kemeny and squared Kemeny. So both of these are Pareto efficient rules. What does Pareto efficient mean? For example, it means if all of the input rankings place some alternative A above B, then the output ranking should also put A above B. You can also define it in different ways. For example, there cannot be a different output ranking that is closer to all the input rankings in terms of Kendall-Tau distance. And it's easy to see that both of these rules will also satisfy Pareto in that sense. Both of these satisfy participation. What does participation mean? For example, if you increase the weight of one of the rankings, then the output ranking must come closer to that ranking. Kind of a monotonicity condition that is satisfied. Solidity proofness means suppose now you're ranking, you're actually a voter, you're a person, you want the output ranking to be close to you. Can you then actually give maybe a different ranking from your truthful one to induce the actual output ranking to be closer? Both of these rules can be manipulated by misreporting your preferences, but Kemeny, not too bad. There's a certain weak form of solidity proofness that it satisfies, whereas squared Kemeny not at all solidity proof. And that's not surprising because all kind of fair rules, proportional rules, have this property. You can always pretend to be really unhappy with the status quo. The rule will feel sorry for you. I mean, you have like a massive square distance and it wants to go closer. Similar, so squared Kemeny behaves like an average. Suppose now we are aggregating numbers together. If I take the median of a bunch of numbers, I cannot manipulate that. By running away from the median stays exactly where it was. Whereas for the average, I do want to run away and be an extremist. And it's also worth mentioning that this property of two-ranking proportionality can be generalized a bit to say what should happen on so-called single crossing profiles. Mention single crossing briefly. Here's an example of this is supposed to be an input profile now, where you can order the input rankings in a natural way, such that there's never a crossing back and then forth again. And on those profiles, you can define what is the median ranking in a simple way, and Kemeny will always pick that median. And you can also define the notion of a mean ranking at the mean position, and the Squared Kemeny rule will pick that, underlining this idea. I mean, Kemeny called them the median and the mean rule, and that was a sensible choice. Okay, so let's talk briefly a bit about computation. Squared Kemeny is NP-complete to compute. Not so surprising, because Kemeny is also NP-complete to compute. There are in factorial many rankings that we're optimizing over. It's close for Kemeny, it's closely related to the feedback arc set problem. Squared Kemeny is NP-complete too, even if we only have 4 rankings in the input with the same weight. So it's just 4 rankings, each of weight 25%. The reduction is very similar as for what I call egalitarian Kemeny here. That's the rule that minimizes the maximum distance between the output ranking and one of the input rankings. And that has been shown to be NP-hard in this nice paper. However, it can be computed using an integer linear program. If you're into fair allocation, and you might know this paper about maximizing Nash welfare, and they have a trick to compute Nash welfare with an ILP, but it's not a big trick. What's the trick? We have this squared objective function. We can just approximate the square function as piecewise linear. We can make all the pieces have length 1, because we're only evaluating the square function at integer points. Also, the distance between 2 rankings is always an integer, and so that's completely exactly correct if you do it like that. Okay, then we've shown that the Kemeny ranking, if you compute it, then it's a 2 approximation to Squared Kemeny. Now, this is not a useful approximation algorithm because the Kemeny ranking itself is hard to compute. So if you want an approximation algorithm, this is a bit of a silly result, but this result also works with epsilon. So if you have an approximation to a Kemeny ranking, then you also have a 2 times worse approximation to Squared Kemeny.
So approximation under which metric?
No, approximation to the score.
Okay.
To the score of the, yeah. I mean, also these decision problems are also in terms of the score with the objective function you want to get. Yeah. But the nice thing is there has been a ton of literature on approximating Kemeny. And so we can turn all of these into 2 times worse approximations to Squared Kemeny. In particular, there's a p-TAS for Kemeny. And so we have a kind of 2 p-TAS for Squared Kemeny. However, is it at all of interest as a result? I don't think so. Because why are we interested in Squared Kemeny? Because it selects the better ranking, a ranking with better properties. It's more in the middle, it interpolates more. Right? And here we say, well, for approximation purposes, we might as well take a completely different ranking. And then on the score is still okay within a factor of 2, but it's not the right ranking. So it's not clear at all that such approximation algorithms would at all give us the desired output. Okay, so I mentioned this ILP with the piecewise linear approximation to the square. That is a lot more expensive to compute though than Kemeny, the normal Kemeny rule. There also a big trick you can apply that you're only looking at the pairwise majority graph. And so essentially the number of voters, like your computational complexity does not grow at all in the number of voters for Kemeny, but for Squared Kemeny, it does. You need to approximate the square function again and again for each of the voters. And so you can see here that the blue lines are computation times for Squared Kemeny. The gray lines are for normal Kemeny. And you can see it's a lot faster. So it is still, these are seconds. So if you have 50 alternatives, then you can still do it in under a minute. But these are not very many different voters. If you go above that, it's quite expensive. And so that limits the applicability of this rule, at least for the moment. I gave you some applications at the start, or news feed or something like that. University rankings probably have 100 or 200 of those. That's quite a lot. On the other hand, the number of voters is actually often small in many of these applications because the voters are the different criteria in that case, and there might only be 2, 3, 4.
What is Gurobi?
It's a new sequence.
Okay, it's the new name of CPlex. Or
yeah, well, some of the original CPlex guys had a falling out with IBM, I think. And,
yeah, they were fired and they decided to make CPlex but better.
Okay.
And it's easier to obtain a license and to install it. And it's faster. So
Okay.
I think few people use CPlex. Okay, so that's that. Then finally, we did some experiments to understand sort of more specifically how the rule behaves. And so let me talk you through a few of those, and we will start with just a detailed example of some input and what's the output. In particular, we've aggregated city rankings. So we took 25 cities and we ranked them based on their GDP per capita, how rich is the city, their air quality, and by their sun hours. And we want to know what's the best city. And oh yes, we can actually see it. I'm happy. And then, so this is our input here. 25 cities ranked in these 3 ways. We've assigned weights 40%, 30%, and 30% to those 3 criteria. And then we plugged it into Kemeny and into the Squared Kemeny rule. And this shows you the difference between the 2 rankings. So, for example, both agree that San Francisco is the best city. Probably means there are some criteria that we forgot to put into our aggregation. Okay, but so what can we learn from this? So first thing we notice is that Kemeny has the same top 5, actually the same top 7 as the GDP ratio, and then like the first time it differs, it actually does the wrong decision. Okay, so this is exactly what I've been hammering home again and again, that Kemeny seems to like the most frequent input ranking it sees. Whereas what does Squared Kemeny do? Yes, it has significant overlap with the top 5. But Zurich and Dublin, it ranks lower. I mean, especially for Dublin. I mean, Dublin is the least sunny city on the list. And so probably it deserves to go down a bit. Whereas Dubai is doing okay in the GDP criterion, and it's doing very well on the sunniness one. So probably if you want to merge them, it deserves to go up a bit further. So intuitively, I mean, probably both of these rankings make sense, but they make sense for somewhat different reasons. Where's Paris here, actually? Oh, what have we done wrong? Okay. Not enough sun, yeah. Okay, then some other simulation results based on random data. So this picture is a bit difficult to explain. So we wanted to visualize, we take a random profile, we wanted to visualize that profile, and then wanted to visualize where is the Kemeny and Squared Kemeny ranking in relation to that profile. And so how can we visualize a profile of rankings? And there's this maps of preferences idea. This is coming out of Krakow and Piotr Faleszewski's group, who have been working a lot on making what they call maps. The first thing they did is they took different random distributions over profiles or different data sets of preferences and put them on a common map so that you can see similar profiles go together. This is actually different. This is maps of preferences, by which they mean just a single profile, and we want to look at that profile, called the microscope, put it under a microscope. And what we do is we take each ranking in the profile, and for each pair of them, we compute their distance. That gives us a metric space over the rankings in that particular profile, and then we just push it into two-dimensional space. Yeah, some PCA type thing. Multi-dimensional scaling is what it's called, so more generality. And then we get such pictures here. But we can also just compute the output rankings of Kemeny and Squared Kemeny and put them into the same space, and so we can sort of see where they are. Okay, so what's happening here is we're sampling a profile in Euclidean space. So we put alternatives in random locations, voters in random location. Voters prefer things that are closer to them. And we're putting them in a disk. And I mean, there's no interesting difference between Squared Kemeny and Kemeny on this. So green is always going to be Squared Kemeny, green for good, and red is going to be Kemeny, red for bad. So the circle one is very similar random distribution, but this time we don't have the disk, but we only have the boundary of the disk. And there we actually have quite an interesting phenomenon where Kemeny is on some point on the boundary and Squared Kemeny is in the center of the circle. Now, why is that? So this is actually the boundary point that just happens to be the most dense in the random profile, because on the circle, for each point on the circle, we also have the complete opposite ranking on the other side of the circle, and they cancel each other out on the Kemeny objective. And so you might as well be wherever the most prominent ranking is. That gives you like little epsilon gain, everything else cancels out. Where Squared Kemeny doesn't want to be too far away from anyone, if possible, and so it goes into the center. And this kind of thing is probably where the 17% example also comes from. Okay, here are two Mallows mixtures. This is a mixture model where there's a bunch of, I think there are more people here, maybe 60% and 40%. I need to look it up. 60% of voters are sampled from one distribution, 40% of voters from another distribution. And in that case, we see Kemeny goes into the center of the bigger cluster, but Squared Kemeny interpolates between the two a bit more. Here it's interesting. It's still the case that there are more points in the bottom left, but the other cluster is more concentrated. This is a concentration parameter. And then Kemeny actually can sometimes prefer to go to the more concentrated one, not the bigger one, the more concentrated one. And these are two data sets from PrefLib. Here, people ranking breakfast items in order of preference. And here, country ranking similar to our city ranking, where there's not as pronounced a difference as in distributions that were particularly chosen to show a difference between the two. Okay, but this way of picturing a profile and the outcomes, it could be misleading because these are not actually two-dimensional things, so maybe something's being hidden. So we tried a different way of visualizing things. So suppose I take a profile that I've actually generated in the Euclidean way by taking the plane, putting alternatives in random positions, putting voters in random positions. Voters prefer alternatives that are closer to them. I can draw such a profile very easily. Here I've only drawn the voters, not the alternatives. And then I could also draw the output ranking. So I take the input profile, I compute Kemeny or Squared Kemeny. Now the output ranking, there might not be any point in the plane that actually induces that ranking perfectly. There's no guarantee for that. But I can take the point that induces a ranking that's almost the same, and I can just optimize that. And this is what happened here. So I've taken the unit disk here, put voters at random spots in the unit disk. I've done that maybe 100 times or 1,000 times and show them all. And then for each of those 100 times, I compute Kemeny and Squared Kemeny and show you where they end up. So this is now an aggregate over 100 sample runs. And here we see that Kemeny and Squared Kemeny don't meaningfully differ on this very well-behaved instance. Just going in the center is typically the right idea. Then here I have a mixture of two Gaussians, same size, and again, they agree where to go. But now I make these Gaussians have different sizes. So this one has maybe 70% or 75% of the voters, 25% of the voters sampled here. And then we can see Kemeny goes into the middle of the larger cluster where Squared Kemeny interpolates between them. And here's a similar picture with 4 clusters, one bigger than the others. Okay. So let me mention some future directions of other things one could do in this type of domain. So we had this idea of the alpha curves where we saw for Kemeny, we had this threshold thing, and for Squared Kemeny, it was a bit smoother. And this kind of idea makes sense in many other collective decision-making problems, where you can look at sort of the happiness of groups in the worst case as a function of the group size. And maybe it's useful to do that in other models. Now, Squared Kemeny is intuitively averages the rankings. And I've often used the word proportionality, by which I wanted to mention the idea of proportional representation as we know it in politics in many countries other than France, where you vote for a party and then the percent of the parliament that's made up by that party is proportional to its vote count. And you can generalize the idea of proportional representation to many other voting situations or voting-like situations. The kind of group fairness notion that says if you have a group of 30% of people, they have the same kind of preferences, then 30% of the outcome should be in accordance to their preferences. Now the idea is proportional representation, is it the same as averaging or is it something different? I'm not sure, that's a more philosophical question. But then little tweaks to our model is to consider other rules other than Squared Kemeny. For example, so Kemeny is based on this pairwise bubble sort Kendall-Tau distance. You can use other distances such as the Spearman foot rule distance. We've squared things, could also cube them, power of 4, power of p. So you can look at other p Kemenys and they will somehow interpolate between majoritarianism and egalitarianism. Then maybe, especially if you're unhappy about the 17% hump, maybe you just need to look at other rules and they might do better. So particularly from recent work on proportional aggregation, then you might get ideas like PAV. And then finally, so Squared Kemeny, we've looked at it in a kind of normative way. What properties does it satisfy? Is it a good rule? Does it behave well? Maybe one can make an epistemic argument for it too. By that I mean, suppose we have a model with the ground truth. There's the right ranking, and we want to discover the correct ranking. Then there is a classic argument for Kemeny, because Kemeny is a maximum likelihood estimator of a certain noise model, the Mallows noise model. And probably one can adapt the Mallows model and make it kind of normal distribution type analogy of Mallows, where you have sort of the squared distance and now than the distance, and then Squared Kemeny should be the MLE for that. And the question is whether it might actually make sense in a ground truth way. Yeah, so these are future directions, and I thank you for your attention.
Are there any questions? Room or on the bridge?
Well, I wanted to ask a question about Spearman, but obviously already because complexity. I don't remember for norm 1 Spearman, is there a name associated to the voting rule or not?
Is what associated?
If you do a voting rule based on the
Spearman
with one norm, has it a name? I don't remember.
I don't think it's a different name. There is some variant that you can compute in polynomial time using some sort of binary bipartite matching. Say again?
Spearman should be polynomial.
Yeah. But then squared Spearman borders rule also is implicated in that. I think maybe squared Spearman is equal to the border rule. I think that's right. And actually border rule, if you plotted some of our pictures, it behind it's a bit more towards the squared Kemeny side. It's still in the two rankings case, it's just like Kemeny where it goes with the majority, but in more complicated things, a bit more compromising.
About the computation of the result, in the case of Kemeny, there is something that helps you a lot. The fact that you can restrict the computation to each strongly connected component of the majority, unweighted majority.
Yeah.
And in fact, in random instances, it doesn't help you, but in a real life application, it helps you a lot because generally in real life,
Condorcet winner at some point, for example.
You have a Condorcet order, and anyway, the computation is over. So of course, I guess that in the case of the Squared Kemeny rule, it's not the case.
No, there's nothing like that you can do because you need to look at each voter individually because you need to know how far away they are in order to see how important it is to make them happier. And so you can't, like in Kemeny, just look at pairs of alternatives and see how well they do against each other. I mean, maybe there's some other trick because I mean, you remember the NP completeness result even holds also, like for Kemeny, for 4 voters already. So that suggests that the voter number is not the thing that makes it hard. We don't know.
You can use embeddings to have approximation, maybe not with theoretical guarantees, but approximations where a kind of geometric resolution will make a nice result in practice. I don't know.
So you cluster the voters, for example.
Yeah, actually, exactly like you did in your curves. Maybe you could do this to predict the actual position of the thing.
Right.
It will not be. It will be hard to theoretically prove.
Yeah.
It will be nice in practice.
Yeah, so it's a bit difficult to know, though there's no obvious measure how close you are to the right answer. Because
compute it, yeah.
Because like just doing well on the objective multiplicative sense is not always, because Kemeny, for example, does already pretty well on that objective and sometimes does not do the right thing. So yeah, it would be interesting whether you can heuristically somehow get good outcomes. I agree.
Or maybe Spearman would be a good approximation.
Yeah, or border even. Yes. Because squared Spearman is
very likely.
Yeah, but it's unsatisfying, I agree.
I have something that is maybe more a remark than a question. During your talk, I talked a lot about a paper by Jean-François Lalliot, which is called the Strange Majority Judgment. I don't know if you know that paper.
Right, yes.
And it's essentially what he shows several bad properties of majority judgment, but one example is that you assume that you have a one-dimensional political space, and that approximately one half of the voters are on the right, approximately one half are on the left. And so if there is a bit more people on the right, then range voting, for example, will put the winner slightly on the right of the origin. Yeah, exactly like that. Yeah, and so it's really the same kind of difference between Kemeny and Squared Kemeny that the one you have between range voting and the majority.
Yes, yeah. Majority judgment goes into the center of the bigger, the bigger block, not in the center overall. Yeah.
What is it?
No, don't use majority judgment as the story.
And I had a stupid random idea, which was that, so essentially when you consider Kemeny, you can think of a 3D tensor with candidates and voters. And for each voter in each pair of candidates, you have the 1 or 0, depending on whether the voter swaps the 2 candidates compared to the ranking that you're considering. And for the usual Kemeny rule, just sum all the components of the matrix. And it's interesting to see it in both directions, because if you see it in one direction, it's essentially the definition that you get for the Kemeny rule. But if you do the sum in the other direction, you see that it amounts to minimize the upper triangular part of the weighted majority matrix.
Yeah.
So and so on and so on and so on. So my random thought was about, so for the squared Kemeny rules, what you do is that you sum over the candidate directions, and then you take the squares. And what happens if you have the stupid ideas of doing it in another
Right.
direction? So
Yeah,
essentially saying that, for example,
I know that Felix Brandt and gang, they looked at this rule, maximal lotteries, and they sometimes look at maximal lotteries cubed, where they first cube all the majority margins. They use cubing because positive and negative, you want to keep that. This is the same. But I don't know what the results are for that. But yeah, so things of this kind of sort have been done a bit, but it probably makes no sense.
if everybody, so thank
you.
Thank you.
Thanks.